Good afternoon and welcome to today's webinar, Machine Guarding Minimum Safety Distance for Guards and Presence Sensing, presented by EHS Today, New Equipment Digest, and Machine Design. My name is Stephanie Valentic, Associate Editor for EHS Today, and in a moment I'll be turning things over to our speakers. I would first like to thank Schmerzel for sponsoring this afternoon's webcast. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the Help button below the slides. We welcome your questions during today's event. Just type your question into the question window on the left side of your screen and hit the Submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Let me now introduce today's speaker. Mike DeRozier is a TÜV certified functional safety engineer for machinery. His 20 years of experience include controls engineering to design, build, and integrate full machine control systems. His safety experience led him to help corporations to develop corporate safety standards, perform machine safeguarding risk assessments, machine safety training and design, as well as implementation of safety systems for all aspects of machinery. Now let me turn things over to our presenter. Mike, the floor is yours.
Thank you, Stephanie. Well, hello, everybody. Appreciate everybody taking some time to attend the webinar today. A lot of you may have attended some of our past webinars. This one's slightly on the different side, where we're focusing really down onto a specific issue when it comes to what we call separating and non-separated guarding, so things like hard guarding and presence sensing devices such as light curtains. What we find in many cases is guards are being misapplied. The intention is there, but not looking at the actual safety distance and knowing that people still have reaching capability of getting hurt. So in this webinar, we really wanted to tackle that subject and utilize two resources with ISO standards, being ISO 13855 and ISO 13857. And we'll talk some more details about those two standards as we talk the different guarding types and looking at safety distances for machinery. When we look at guarding types, we break them into, as I just mentioned, separating versus non-separating. And what does that really mean? Separating is considered hard guards, whether they be fixed guards that are permanently mounted to a post onto a machine. They're not removable by operators. And then you have movable guards, such as swing doors, counterbalance doors, sliders, lift-off covers. And as you know, with those type of guards, you have to have some type of safety interlock switch on them. But in both of those cases with fixed and movable guards, the ability of reaching through, around, under the guard becomes an issue. And that becomes clear in dealing with safety distances. The standard for that is specifically ISO 13857, as you see on the slide there. When we talk non-separating, so I listed just a few examples, light curtains, two-hand control, mat, but it's also bumpers and edges and laser scanners, anything that detects presence of people but is not a physical barrier guard. We're not able to use the same charts that we see in ISO 13857 because where a guard physically stops you, a hard guard physically stops you from penetrating so far, you can have a fixed chart with a distance. With non-separating guards such as light curtains and two-hand control, when you initiate that stop by breaking the light curtain, for example, it takes more to determine safety distance because the light curtain is not physically stopping you. You're going all the way in, and you're going to continue going. The idea behind things like presence sensing devices is that quick, easy access. But an important factor in safety distance is looking at stop time of the machine, and we utilize ISO 13855 as the design standard for safety distances based off of calculations. There's formulas in there based off of the devices, the way they're mounted, and it gives you a good idea of where safety devices such as light curtains need to be positioned relative to safety distance for the hazard. The first I'm going to talk about would be the fixed or movable guards. And I think everybody on the line has probably seen signs exactly like this, similar to this. You see the warning signs on the machine, the caution signs. You see right there, warning, automatic start, keep hands clear at all times. But even that one on the bottom, warning, do not reach over or under guards. And in cases like that, when you see those signs, it might be a trigger that there might be an issue with safety distance if you have that reaching capability. So what we're looking at is when you see the picture in the top right-hand corner of the slide, you can have some sort of perimeter fence as an example, whether it's a solid Lexan barrier, whether it's made out of aluminum extrusion, welded steel, clipped in, bolted in. It's still some form of hard guarding to protect people from getting into any hazardous motion or energy into a machine to keep them safe. But part of what we have to look at with the hard guarding is our reaching capability. And it's not just reaching through the guard, because a solid Lexan cover, we can't just reach in up through it. It's a solid piece of material. But as you see in the picture, we do have guards such as mesh that we have to be concerned with reaching through. But what about reaching over the top? If the guard is not high enough based off of where the hazard is, and I can reach right over top of the guard, I could potentially get my hand into a hazardous situation if that fence is mounted too close to the hazard point. Excuse me. Reaching around. We have seen cases where we've had the best of intentions, or the customer had the best of intentions. They installed a fence such as this with an access door to protect from identified hazards they found during their risk assessment process. And as we're walking through, they had these new guards installed, and the one aspect that they didn't look at is the fact that if you look at that picture in the top right again, you'll see that you have the mesh clipped on the left side of that post, but there's nothing clipped on the right side. My ability to reach around the guard. Reaching under the guard, sometimes guards are too high, even though they may only be 6 inches off the floor, which a body cannot reach through there, but your hand and arm can still reach underneath the guard. Can you get to any hazard points at that particular case? So being able to review what that safety distance is and utilize something like ISO 13857 is going to be a key benefit of ensuring that you have proper safety distance. So when we look at the next slide here, just showed you a couple of examples with the picture on the left, hand reaching over top of the guard, or the middle picture, the hand reaching around the post through the guard. What's my reaching capability of getting to that hazard? What is the safety distance? And that could be I'm still stopped up to my body, but if it doesn't stop my body from going in there, how effective is that guard at that point in time? The last picture, being the picture on the right, is reaching through. When you have opening sizes in the guard, slots, squares, what's your depth penetration of that guard? How far can you reach through before the guard physically stops you? So what we wanted to cover is a couple of the examples right out of ISO 13857. This particular example, what we're showing, is the chart that they have in the standard with the basis of reaching over with a high potential risk factor. When you look at your risk assessment, you have a high risk. What should your safety distances really be? So you can see with the bottom picture with the hand reaching over top of the guard, what's my capability of reaching the hazard? So when you look at the height of the hazard versus the height of the guard, you look at the chart and you see that your height of the hazard is your first column all the way on the left, and the top row gives you the height of the guard, what they're calling the protective structure. Draw a line, and that'll give you your safety distance, which you'll see in that little figurine drawing, the C. With that C, that is the safety distance, meaning how far away does that guard have to be from that hazard point at that given point of time. I will come back and look at some additional examples, but with this particular one example we can say if the height of your hazard is 1,200 millimeters off of the floor. So you scroll down that left-hand column at 1,200 millimeters, but the height of your guard is, say, 1,800 millimeters. Well, then your safety distance, if you go across the row and match it up with 1,800, you'll see that our safety distance actually has to be 700 millimeters away. Now, given this is an ISO standard, you'll see all the calculations and distances are all determined in millimeters. For those not familiar or as comfortable with the metric system, just to give you an idea, if you want to convert in your head or using a calculator, 25.4 millimeters is equal to 1 inch. If you're just looking for just a rough number just for conversations, it's 25 millimeters to an inch, or you can say for every 100 millimeters is 4 inches. Gives you just a quick rough estimate calculation just to give you an idea of what that is. So if you think about 700 millimeters, 7 times 4 is about 28 inches of safety distance based off of the height of that structure as well as the height of the hazard. So whichever one you're more comfortable with, but what you're going to see in the slides today, because this is what the standards call out, they're all in millimeter dimensions. Next example is the ability of reaching around, such as we show in the picture. If you can reach around the guard, but your torso, your body is able to stop you, this is one of the charts that says, based off of that, what's your safety distance based off of your reaching capability from being supported at your shoulder, to your elbow, to your wrist, to your knuckles, and they give you some different numbers associated with that. So when you look at that top one being reaching through and stopping at your body, what you'll see is the safety distance is equal to or greater than 850 millimeters. What does that roughly come out to? It comes out to around the 35 inches. And if anybody in the United States has ever heard of the 3-foot rule, which is 3 feet or 36 inches, that's what it's really representing, is you're being able to stop at your torso, and the average reaching distance wouldn't be more than 3 feet. So you have a 3-foot safety distance when you're creating tunnels, for example, off the entrances or exits to the machine to prevent that reach-in. But as you can see, that's where that number comes from, is the average human study and the reaching capability of reaching through or around the guard with being stopped up to your body. The next one, which comes really important, is we see guards with holes in them, whether they're slotted, square, or round, as you see in the charts up here. You'll see that there are certain safety distances that apply based off of that opening size and your reaching capability. How you would actually read this chart is you would look at your opening size, which you see is the third column. What's your opening size in millimeters? Once you get down to that range, you would go across based off of whether you had a slotted, square, or round opening, and that'll give you your safety distances. On the next couple slides, I'm going to show you some examples of utilizing this particular chart based off of opening sizes. So bear with me here. So when you see across the top, it said slotted, square, or round. These are just some examples of what that means. So the picture on the left is your slotted opening. Picture on the middle is your square, and the one on the right is round. So you just have a perf steel or flat and expanded metal or a wire mesh. But where are you actually taking those measurements? And I know they might be a little hard to see in the PowerPoint, but in each picture, if you look at where the red arrows are drawn, what are you taking the measurement of? I think it's pretty clear. On the round, it's just the diameter of the hole. On the square, you're not going diagonal. You're going either up, down, or left, right. What is that spacing from end to end? It's going to be the same up, down, left, right because of the square opening. The rectangular comes into question sometimes. Where do you actually take the measurement? And a lot of times people think you're actually taking the measurement, and if you look at that particular picture, is from left to right. It's actually up and down. It's the width of the slot or rectangular opening, not the length. Because when you look at these charts, what is it actually considering? It's not a flat profile. Your fingers, your hand, your arm is not flat. It's round. It has shape to it. So what is the minimum that your fingers can get through and have your limitation? And it's going to be on the width side of that slotted opening. So jumping back to the chart, I'm going to give you a couple of examples here. The first one is when you have a slotted opening, and let's say the length of the slot is 100 millimeters. The width of the slot is 19 millimeters. So if you look at the chart on the right, go through down to your opening size, and you see anything from 12 up to 20 millimeters. That's where our 19 millimeters is falling, and we have it slotted opening. So our safety distance is going to be equal to or greater than 120 millimeters, which is roughly approximately 5 inches of safety distance. And so what they're saying is your hand can only go so far, up to about 5 inches, with that 19 millimeter gap in the fencing itself. Staying with slotted guarding with these examples, let's say if we increase the width of that slot from 19 millimeters to 24. If we go from 20 up to 30, we have a huge jump. We went from 120 millimeter safety distance to 850 millimeter safety distance. And that seems like it's very drastic and it's a lot for a safety distance. But based off of average human studies is where this came from. The Standards Committee pulled this from. And they basically say in a slot up to 30 millimeters, potentially somebody can reach their whole hand all the way through up to their arm, up to their torso. There are some small people out there that have that reaching capability or that flexibility of being able to get their whole hand and arm into those slots. I know it sounds a little bit crazy, but there is a note, and that note takes us to our next slide. If the length of the slot went from 100 millimeters down to 48 millimeters, what you see is we're still at a 24 millimeter width. So when we go to our opening size from 20 to 30 millimeters, we still see 850, but there's a note A right next to 850. And I'm not sure if you're able to read it on your slides, but it's definitely in the standard because this is an extract right from the standard. It's telling you that note A is if the length of your slot is equal to or less than 65 millimeters, your thumb now acts as a stop, meaning the average human hand studies, you're not getting a hand in from 65 millimeters, including your thumb, so your thumb is going to act as stop as a guard. So now you can reduce that safety distance to 200 millimeters. Why do I bring that up? It's like any other standards, you really have to read through the standard, and sometimes you have to read through the fine print to make sure you're applying the proper safety distance. Because in some cases, like you see this one here, 850 millimeters does seem a little bit ridiculous, but they take a realistic approach to say, hey, if you are less than 65, go ahead and reduce it to 200. And as Stephanie mentioned, if you have questions on any of that, of what I just covered, go ahead and type it in your Q&A field, and we'll get to it at the end of the session here. The next set of devices we're going to talk about would be the non-separating or the presence sensing devices. And as we mentioned, a hard guard physically stops you. You're only going to go so far on a hard guard, whether it's reaching over, under, or through, it's physically stopping you. But things like light curtains and mats and two-hand control does not stop you. You are breaking that beam or letting your hand off of the buttons or you're stepping on that mat, but it doesn't mean you can't go any further. You're still reaching into the machine at that point. So what are some of the considerations that we have to take into account as we read through and apply ISO 13855, which is the standard for calculating safety distance for presence sensing devices? When we look at these design considerations, you can see in the bullet points there, one of the first things is motion has to stop anywhere within a machine cycle. Things like full revolution presses or riveters, where they have a little dog ear that releases, it goes a full revolution. Sometimes you'll see that somebody may have applied two-hand control or light curtains to the front of it to gain easy access to it. But in reality is because it still goes all the way in its cycle and it's relying on that little dog ear to capture it. It can miss. It can keep firing. It's not a good application for presence sensing device. As soon as you initiate the stop, you have to get that to stop anywhere within the cycle and not let it finish its cycle. Some machines, if you have inconsistent stopping times, and what we mean by that is you can have a machine that stops when you do a stop time measurement in 50 milliseconds. The next one is 30 milliseconds. But then the next one is 270 milliseconds. The next one's a second and a half. The next one is 25 milliseconds. When you have a huge variation of actual stop times based off of the performance of the machine, you need to question, is that a good application for a presence sensing device? Because then how do you effectively install it to the proper safety distance? Do you have reflective surfaces that can interfere with light curtains and bounce beams around? The fact is, severe environments, so laser scanners susceptible to smoke and fly-in debris if they're not installed properly. No protection against flying objects, meaning if your machine has a risk of ejection of parts, the hard guard may be designed in a way where it physically stops that ejection. A device like a light curtain, because it's an invisible wall, does not stop you. It's an invisible infrared beams. That's coming through that light curtain at you. But the last part, which is really important, is how you determine the machine response time. What is the response time? So when we look at ISO 13855, there's a few factors that it takes into place. And there's different formulas based off of the type of device you're using and how it's installed. So what is it looking at? Object resolution. It's got approach speed. What direction? Are you coming in vertically, horizontally? Is the device angled? So what's the position and your reaching capability? As you see now, we have a formula. S equals K times T plus C. What does that really mean? What do those letters represent? S is the hand speed constant. And the standard specifically gives you those hand speed constants that you use based off of the device and the installation. I'm sorry, S is the safety distance. K is the hand speed constant for your ability to how fast can your hand or your legs penetrate that safety device. T is your stopping time of the machine. How long does it take to physically stop the machine as a result? And then C, what they're calling intrusion distance, is we hear a lot more in the U.S. as depth penetration factor. How far can you potentially go into that device before you're guaranteed to trip that? So in the next couple slides, we'll talk a little bit more about that as well. So we look at some examples of the formulas. It's not just one formula. And unfortunately, in a lot of standards, you will see one formula called out. You'll see a range of hand speed constants that you use. In this particular case, if we look at the first two formulas, they use a hand speed constant of either 2,000 millimeters a second or 1,600 millimeters a second. These two formulas typically have to do with light curtains mounted in a vertical direction. You see D, which is the object resolution, the detection. So are you using a 14 millimeter or a 30 millimeter resolution light curtain as an example? T is your stop time in the machine. So why did they have two formulas? Well, when you read through the standard, what they're actually telling you is you start off using the 2,000 millimeters a second, but once you go beyond a calculation of 500 millimeters, which is roughly about 25 inches, they're telling you can recalculate based off of the slower hand speed based off of distance. So you can recalculate using 1,600 millimeters a second, but you cannot be any closer than 500. Believe me, I know and realize it's hard hearing that over a webinar, but this is where acquiring ISO 13855 and 13857 from the ISO organization, or you can buy these standards on the ANSI organization on their online store. It's important to have these standards so you can read through them and properly apply the safety distances. But when you look at some of the other formulas, such as that third one down, that 850 may look familiar because we saw it in another slide. It's the reaching capability, and it's a torso. Well, when you look at things like light grids, where your whole hand and arm can go through in between beams, but it's not until your body actually trips the beams, well, whatever our stop time is, we have to add that additional 850 because of reaching capability. The next one down, an example of that would be safety mats or light curtains mounted horizontally on the floor. When you look at your approach, your ability to step on the mat and your reaching capability, where you can bend over as well as reach, that's why that's increased to 1,200. The next one, we're dealing with height, is adjusting the height, such as a laser scanner or a horizontal light curtain, where you can move higher off the floor, reduces your reaching capability. The last one is an example of two-hand control. But again, the ISO 13855 will give you those details of, based off of the device, which formula would you use, what would you apply. I know I threw a lot of formulas at you. Don't expect you to remember it. The standards cover it. But there are some aspects with the standards that sorry, had a little note. Some aspects with the standards that we wanted to cover. Those aspects being depth penetration factor. What do we really mean by depth penetration factor, or what the standard specifically calls intrusion distance? When you see the picture on the left, simulating the front of a light curtain, if you look at the hand going through, the little red circles represent one of the or the beams inside the light curtain, the infrared beams. And if you see that hand starting to go through that light curtain, the fingers are actually going in between beams. So if you think about a 30 millimeter resolution light curtain, which resolution means a minimum object diameter that can detect through the entire field. Anything smaller than that, you can go potentially between beams. So if your hand, as a worst case scenario, can go between beams, the beams, how far can your fingers penetrate in before you're guaranteed to trip the beam right above your hand or right below your hand? And that's where those safety distance formulas on the previous slide, the additional depth penetration factor, it shows you a formula of 8 multiplied by the object resolution minus 14. So if we have a 30 millimeter resolution light curtain, 30 minus 14 gives us 16. 16 times 8 gives us 128 millimeters. So whatever we calculate with hand speed and stop time, we're adding an additional 128 millimeters, roughly about 5.5 inches, because that's representing your hand can potentially go in about 5 inches or so before you're guaranteed to trip the beam above or below. Same thing if you look at the example of a safety mat. The person about to walk on the safety mat there, but right at the edge of that safety mat, if you think about their arms stretching out and their body bending over, they can penetrate so far. And what the safety distance additional depth penetration factor is called out is the 1,200 millimeters, saying you can potentially reach roughly 48 inches before you have to step on that mat to initiate this shutdown of the machine. So that's the additional measurement that has to be added to that. The next thing with it is the stop time of the machine itself, where the standard ISO 13855 gives you some specific criteria as far as when do you use this hand speed versus this one? What do you add for depth penetration factor? The one value that is not given is stop time of the machine, because that's the value that has to be figured out. There's 2 ways to do it. Calculate based off of knowing the components you have in your machine and any of the response time of those components or your system. So, for example, if you have a light curtain installed on your machine, you know by looking at the manufacturer's installation instructions what is the response time of that light curtain in shutting its outputs down. It may be 15 milliseconds as an example. That light curtain is wired into a safety monitoring relay or a safety controller. That response time is given by the manufacturer as 20 milliseconds. So now we got 20 plus 15, we're at 35 milliseconds from the reaction of those outputs. Those outputs are shutting down contactors to shut down a motor. Well, the response time of those output contactors, maybe that's 25 milliseconds. So as you can see, we're adding up the components along the chain, which getting response time of components may not be that difficult, but knowing what the stop time is of the actual motion, whether it be a motor, if you can calculate the dynamics and the mechanical aspects, such as because the motor is connected to a gearbox, it's going to take X number of milliseconds to stop, or the motor is a direct drive motor and there's very little mechanical resistance that it's going to keep coasting to a stop without any braking mechanism in there. Fluid power, such as pneumatics and hydraulics. The size of your lines versus the flow rate and the response time of the valves and how much it exhausts back out to create a stop on that cylinder or dump back the tank. Are you able to calculate that out? And if you are, that's great. You have a calculated stop time, but accommodate for mechanical wear. and you can do a calculated stop time. Unfortunately, what we find is a lot of times trying to calculate is either extremely difficult or maybe impossible for people to be able to do, especially given the age of the machine and the component wear. So the other aspect that you can do instead of calculation is measure. There are several stop time analyzers out there on the market. Some are, handheld devices. Some are computer-based with a communication module. The ones you see pictured here is a PC or laptop-based software system that communicates with that module. You hook up to encoders, triggers, flags, and you actually take stop time measurements as a result. The whole idea, when you look at that, is it gives you a much more accurate stop time that you can develop a report for and put those numbers in those calculations based off of ISO 13855 and get an accurate safety distance, which that safety distance can be checked. When we look at that, if you try to guess, we say I have a note here, guessing can lead to an injury. There are times where we've seen people try to use a stopwatch. They hit the button and hit the stopwatch and wait till they see no motion and hit it again. Unfortunately, you got human response time in there. You're not going to be extremely accurate when it comes to that. And the more accurate you are, the better it's going to be. You can think worst case scenario, it's going to be, maybe the machine typically stops in 200 milliseconds. We're just going to throw 2 seconds on there to be safe. What you're going to see in the next slide is a time difference is very, very critical and has a huge impact on safety distance. The other aspect is the change in time. As we said, a small change can have that significant impact resistance on proper safety distance. So guessing doesn't work. What do we mean by that? Well, when you look at this slide here, we're showing 2 different safety calculations. This is a vertical light curtain using a 14 millimeter resolution object detectability. Based off of 14 millimeter resolution, if you see the picture on the left, that number 3 there, that's the actual stop time of the machine. We plugged in here 100 milliseconds. Well, at 100 millisecond stop time with a 14 millimeter resolution light curtain, our actual safety distance is 200 millimeters, or roughly about 8 inches, which seems very realistic and practical. But knowing that stop time is important because even at 100 milliseconds, you need to be 8 inches away from the hazard point. And light curtains are probably one of the most misapplied safety devices because they ended up replacing doors and they had a nice solid frame to attach to, not realizing the light curtain may have been mounted too close. The picture on the right, we just changed the stop time from 100 milliseconds to 1 second. In the grand scheme of things, you think of 1 second. 1 second is not a lot of time. We're only talking 900 milliseconds of difference here. And at 900 milliseconds of difference, you will see the impact go from a safety distance of 200 millimeters up to 1,600 millimeters of safety distance. So a real rough approximate estimate in inches, 16 times 4, you're at 64 inches safety distance. So we went from approximately 8 inches to 64 inches away, not from the edge of the machine, but from wherever the hazard point is located at. So having an actual stop time measurement is extremely important to ensure you got proper safety distance, but not only proper safety distance, a practical safety distance. Meaning if you can get 100 millisecond stop time where it's more practical and usable in real life, which you may find many of your machines are, great. But if you guess at it and say 500 milliseconds, you'll see that it'll have a significant impact on what your true safety distance is when you plug into these formulas. So at a 14 millimeter resolution, we go from 200 to 1,600. And just to show you a comparison to a 30 millimeter resolution, because your object detectability is increased, our 100 milliseconds, we have to add that additional depth penetration factor. If you remember, we said the fingers going between beams was an additional 128 millimeters, which is why we now see a safety distance of 328 millimeters. And the 1 second, same thing, it was at 1600. We had to add that additional 128, so it's now 1728 milliseconds. What does it look like when it comes to two-hand control? Well, two-hand control, you'll see at 100 versus 1,000, where do the two-hand palm buttons need to be placed? From 410 millimeters to 1,850 millimeters. So it could be significant knowing what that stop time is for positioning your two-hand control. It's not just right at the press if it takes forever to stop. The last example I wanted to show you was the safety mats. Safety mats are a phenomenal device, but they're not typically used as primary protection because of how big the mat needs to be. They're used as supplementary, secondary protection inside cells, around areas that people can't normally get to. But without having any guarding or any light curtains or anything like that, trying to use a mat as a primary protection may be perfectly fine, but you don't know that until you actually plug in the safety distance formula. Because even at 100 milliseconds, if we take our 1600 times our 100 milliseconds, we have 160 millimeters. We have to add an additional 1200 to that. So our safety distance is 1360 millimeters, which comes out to roughly 26, 52, about 54 inches safety distance roughly. But an increase in stop time up to 1 second, that's a huge number, and the matches have to be monsters as a primary protection, and gets a little crazy, impedes aisleways. So they were just some quick examples of calculations using the safety distance formula. Why did I go into more detail with those? When you look at hard guarding versus presence sensing devices, the hard guarding, you have physical formulas. The presence sensing devices, you don't have physical, you have physical charts that you can pull a number from. With presence sensing devices, you have specific formulas that you have to tie in, and you need to know proper safety distance as a result. How often should you perform a stop time analysis? ISO 13855 does not give any specific time intervals from anything that I read. Normally what you find is the testing time is usually have recommendations by the manufacturer. So as an example, you may pull a installation instructions operation manual for the light curtain. You look at the back page for the checklist, the PMs, how often should you check it. Typically you'll see a test time of every 6 months to know that the machine hasn't worn down and hasn't taken longer to stop, which you're maintaining proper safety distance as a result. Again, hard guarding, there's no variation because even if it stops longer, you still only have a certain reaching capability. Things like light curtains, you have additional reaching. So the additional measure that they get into and talk about is you can't just take one measurement. What the standard calls out is you have to take at least 10 measurements, and based off of those 10 measurements, you're either using the maximum or you're using the average plus 3 standard deviations, whichever is greater. And that'll give you more of a accurate safety distance calculation. So at this point, I know this was more geared and specific to installation and safety distances, but it was an important topic we felt was definitely needed, knowing that when you install guards, because we're seeing a lot of people and customers that have definitely the best of intentions. They do not want to see people get hurt, so they're installing the guarding, they're adding these safety devices, and they're spending money doing that and maintaining their productivity. The last thing that you want to see is somebody still get hurt after you put all these efforts into because the devices were not installed properly. So we wanted to bring more of an awareness of that to really help people make sure that when you go through that, they are being installed per the safety distances that you can document. So, Stephanie, at this time, let's pass back to you and open up the questions.
All right, thank you. A few of you have already submitted questions, but if you haven't had a chance to, it should be located in the, a window should be located on the left side of your presentation console. So for our first question, how do these distances compare of separated guards compare to the table of distances OSHA specifies in subpart O?
Okay. And, excuse me, what we found is some variations between what was in the OSHA standard, what is in some of the ANSI standards. Some of the ANSI standards have their own charts, as well as they recommend the use of ISO 13857 in some of their standards, and then ISO 13857. There's definitely variations from what I know at this point in time. Looking at those variations, a lot of the OSHA numbers, the what people know as the OSHA gotcha stick, comes from the PowerPress standard 1910.217, and those safety distances were pulled from a study done by Liberty Mutual back in the early 80s and hasn't really been updated much since, where the 13857 accommodates for more of the modern-day workforce. So there tend to be some slight changes. From the things that I have found in looking at the comparison, the biggest changes I see is some of the smaller opening size at the beginning side of it. On the ISO tends to need to be a little bit further away, and the reason being is when you look at the modern workforce, there's a lot more women in the workforce, and the average female versus the average male, the average female tends to have smaller hands than the average male, so they can get into tighter areas a little bit further than the average male. So the studies accommodate for that. Usually what I end up recommending is whatever standard you're going to go with when it comes to the safety distances. I spoke specifically at 13857. If a specific ANSI one with their chart applies to your specific machine, by all means use that. If OSHA seems to be a better fit for you for the machine that you're working with, I would definitely look at that and compare it to 13857. But if you're using some sort of safety distance chart that you can document, you at least know that you have some sort of safety distance in place. And that's, to me, more of the key than anything else. I'm not specifically saying you must and you have to use ISO 13857. It is the standard that a lot of other standards are actually recommending and going by. But whatever standard you use, document what you're using and why you're using it. To me, it becomes more of an issue of the reaching capability, because when you look at that reaching chart in the 1910.217 for OSHA for power presses, it's actually the chart for reaching through, but it doesn't differentiate between slotted, square, or round opening sizes or irregular sizes, and it doesn't accommodate for the reaching capability of reaching over, under, around, and that's where 13857 really expands on. So I like 13857 because it has a lot more details, but it's not dismissing because OSHA is our governing body in the United States. You definitely want to utilize the charts that they're going by, but look at that comparison. You will see some slight differences, but ultimately what we end up finding is a drastic difference in installation because no charts were being used. If you're using one of them, at least you're getting to a proper safety distance. The problem comes down to when you're not using any safety distance chart, the guard ends up being way too close, and you have a risk of serious injury.
All right. Next question is, what about U.S. standards such as ANSI?
I think we just covered that in the last one. ANSI standards, many of the ANSI standards that I have read through, they refer back to ISO 13857 for safety distance, especially any of the ones that have been revised in the last several years. There are some ANSI standards that have a different opening size reach-in capability. I think B11.19 is an example where it's utilizing some of the human studies done recently by Liberty Mutual back, I want to say in the early 2000s, but don't quote me on that, that there are some differences in there as well. But it comes down to many of those ANSI standards and ISO standards are not incorporated into reference in the law by OSHA, so you won't get fined for violating those standards because they're industry voluntary consensus standard, but you're encouraged to use them as such.
Okay. How does time affect safety distance of an EStop?
How does time affect safety distance of an EStop? With EStop, what they're looking more at on the EStop devices is it's more of some machines and their reaching capability, that because the machine guarding is the primary guard, so whether it be a hard guard or a light curtain, having that safety, that EStop at a proper safety distance. So if that becomes the primary protection, you don't have the reaching capability into the machine to actuate the EStops. Normally, even though you see that in there, because EStops are secondary and they're outside the guard, you don't normally see a safety distance on the EStop, even though it's considered a presence sensing device. It's the hard guard of the light curtain that becomes more of the issue.
All right. Is the calculator tool available for download?
The calculator tool, the one that you saw in the images, is part of the software package from the stop time analyzer that we use. So if you purchase a stop time analyzer from a manufacturer, most of them with their software tools have those calculators in them to use. So I just took snapshots, or I should say screenshots, of those numbers based off of using the software tool that we have. It's not available for free download. You have to purchase a stop time analyzer. But I know it becomes a quick, simple, easy tool to have that calculator. It's nothing more, it's just a nice graphical representation of something that you can create in Excel. You can create the same formulas in Excel and just create those different tabs or the screenshots, but you just have to create at that point in time. Otherwise, if it's something that you're interested in getting that stop time measurement, whether you hire somebody like us to do stop time measurements, but a lot of times customers may want to have their own tool and they can get that software and have the calculator in there and be able to print out the reports.
Okay. When using safety mats, is there a minimum depth that the mat has to extend from the safe distance? I assume it has to go all the way to the hazard, but I cannot find it in the standards.
Okay, I'm sorry, Stephanie, I missed you there, broke up. Can you repeat that for me?
Okay. When using safety mats, is there a minimum depth that the mat has to extend from the safe distance? I assume it has to go all the way to the hazard, but I cannot find it in the standards.
Okay, if I'm understanding the question right, and if I don't, please go ahead and type in and clarify for me. With safety mats, and this question may have came in beforehand, but with safety mats, what you have to do is the depth of the mat being, if you have an example where you're at the edge of a machine and somebody's trying to put a 4-foot wide by 2-foot depth to the machine, that doesn't meet safety distances, because when you read 13855, when you're using a mat, which is on that horizontal surface, the formula takes that hand speed of 1,600 millimeters multiplied by the stop time of the machine, and you add 1,200 millimeters to it. So that 1,200 millimeters is the additional depth required based off of reaching capability. But keep in mind with all of these, not just mats, it's mats, light curtains, two-hand control, all of them, it's not to the edge of the machine, it's to the edge of the hazard. So in that mat calculation at the 1,200 millimeters, if we stop in 100 milliseconds, we said 1,600 times 0.1, being 100 milliseconds, is 160 millimeters plus the 1,200. So our safety distance from the start of the edge of the mat to the hazard needs to be 1,360 millimeters. So at 1,360 millimeters, that's not the edge of the machine. That's the start of the mat. So if the hazard is 300 millimeters into the machine, well, 1,360 minus 300 is 1,060. So your mat needs to be 1,060 millimeters wide from the active area to the edge of the machine, because you have the additional 300 byte distance, because the hazard is 300 millimeters into the machine. So I hope I understood that question right and answered that properly for the person that asked.
Okay. What do I do about guards I've already installed and find that they do not meet the standards?
Okay, these get a little bit trickier with guards that you have installed. When you use the ISO 13857 as your standard template and you pull up the charts, if the problem is I can reach around the guard, how do you add additional guarding? Can you add filler panels? Sometimes people think, well, I got to rip down the guarding and replace it all with all new guarding. If your guarding is fine, it might be extending the guarding. Like some guarding manufacturers, you can add extension panels to it and grow them for reaching capability. If it's reaching under, you might need to add a filler panel underneath to keep people from reaching under. If it's reaching around, it might be adding a panel but in 90 degrees to the guard to keep you from reaching around the guard. The harder one comes down to is if your safety distance are fine for reaching over, under, and around, but it's reaching through that becomes the problem. Well, if we're reaching through a guard and our guard is way too close, you either need to start backing the guard up or you may need to change the guard material. So instead of a wire mesh, for example, maybe it needs to be a Lexan panel or plexiglass or a steel panel that gets installed, because you cannot reach through that at that point in time. Keep your posts where they are, change the panel out as a result to get your safety distance.
Okay, here. Let's see. It looks like we're about out of time. We're at the top of the hour. If we did not get to your question today, we will be providing all of the questions to Mike so that he can answer outside of this live broadcast. On behalf of EHS Today, New Equipment Digest, and Machine Design, I would like to thank our speaker, Mike, for his presentation this afternoon. I would also like to thank Schmerzel for making this webinar possible. I would also like to thank you, our audience, for your time and attention. We hope that you found today's event valuable and will return for future webcasts. Have a great remainder of the day.